All right, so far so good with this. We've got two different noises, but maybe we want to scale the whole thing overall. That'd be pretty common. So let's add another parameter, and we'll just do that. Let's just say overall, overall scale. So the overall scale, we can just throw right into our main multiply thing here. Scale comes into 0, of course. If I bring it back to 1, it's like that. This isn't that big, but this that might be too small. I don't know. I mean, going down to 0 will basically turn it back into the original sphere. Let's see. So let's start at half. Let's just start at half. That's pretty good. We'll also be able to control the velocity from this particle sim. But anyway, as I scrub through, you can see how I'm getting all these cool extreme shapes like that. One thing though that I would like to see is while this is cool, it's kind of just, you know, still kind of round. I think it would make sense that if I have my laser coming in, hits the ground, and I already have this thing here, I know that the velocity is coming from this direction, like that, right? I would expect that it hits the ground here, and then a lot of it reflects back out, like going the same direction because of momentum, but bouncing, reflecting really off the ground. And right now it's not really doing that. It's just doing, and that's why I've called this radial. It's just kind of just going out. There's no bias in any particular direction. So let's add some, you know, bias to it. So going back into design, draw it back in here. And again, we can see if I put the normals on, you can see these are going to be the velocities that end up getting sourced in. So let's take the incoming velocity and let's normalize it. Normalizing, if you don't remember, takes a vector and turns it into a unit vector. So no matter how fast the velocity is, it's going to take all the speed out, and it's just going to be the direction instead. So just a simple unit vector, the direction that we can use to figure other stuff out. So, for example, we could figure out the reflection. Now, a reflection, as you can see here, reflect VOP. A reflection is going to take, as you can see in this image, it wants an incoming velocity, that's this little arrow here. It's going to hit the ground, which is defined by its normal, which in the case of our ground is going to be 0, 1, 0. 1 being in the y component, meaning it's pointing straight up. So we got the velocity coming in, that vector. We're going to have the up vector, and this thing is going to return us the reflection, which is what we want. So the direction is that, the now normalized velocity, and we want the normal of the surface. We already know, again, what it is, 0, 1, 0. So let's drop down a constant that we can reuse. This constant we'll call up, and it's going to be a vector, 0, 1, 0, like we said, and pass that into that. So now this will be the reflection. And that reflection, if I just want to look at it here for a minute, I'm gonna pipe it in to the normal, just so we can see it, and I'm gonna turn off this displacement, just so we can see. We'll turn it back on later. So here's our reflected, boing, our reflected velocity. If I didn't have this on, that would be our incoming velocity, you know, coming down from the launcher. Now that we did the reflection, I have this, which points up from the ground, but in the same momentum of the incoming velocity. Cool. So once again, I'm going to box this up, give it a cool color, and I'll say reflect. Great. So that's all well and good, but what can I really do with that? So now that I have the reflected area, should I add these vectors on to it? You could do that. I think a much more elegant way is to rely on, let's just rely on the velocities that we're already getting. The ones that we get from all of our radial goodness here. Let's just scale up those vectors. So let me put this back here. So here's our crazy velocity thing that we've worked on so far. This is what we've been making with our 2 layers of noise. What I want to do is I just want to play up these vectors in this area, in the reflection side of it. We already have a sense of what the reflection looks like. We know it's mostly on this side. But how can we turn that into a kind of a mask for this so that we can just identify this region? Well, the way we can do that is a dot product. A dot product simply says, give me 2 vectors and I will compare them to each other. If they're pointing the same way and they're the same size, then you get a 1. If they are opposite of each other, you get a 0, or rather you get a -1. If they are perpendicular to each other, which would be the halfway in between solution, you get a 0. So let me show you what I mean. We know that we have normals. We know that we have regular sphere normals coming into this, right? We made them. Here they are. They point out from the surface. Now we also know that we have those reflection normals that we just saw a moment ago, the ones that point out this way. That reflection direction, I should say. So those are the 2 directions that I want to compare. I want to say, hey, are the normals on the surface the same as the reflection? If so, mark all those little points with 1s and the other sides with -1s and kind of go between those 2 things. And that's what the dot product will give us. So to prove that, I'll just take the result now, plug that into the color, and there you have it. We can see that the backside here is 0 or less, and then up here it's a greater than 0. And if we wanted to really see that again, I'm going to take the normal back, plug it back into the reflection. So you can see, there you go. The whole thing turned black because the normals end up breaking the color that we just did. But so just remember, the reflection's pointing that way, which means that's where we want, and that's what we're getting with the dot product. This is the area that we're going to want to accentuate. So right now, I can say, take the result of that, throw that into the main multiplier. And let's look at what that gets us. And as you can see, now, sure enough, we're getting this strong exaggeration in this direction. Problem is, it's also collapsing this side of it because of all those -1s. See how it's actually pointing inwards now? That's no good. We don't want that. So, put this back here. All right. You can see how they're literally pointing inside of it now. Which, I don't know, maybe that's what you might want. That's not what I want. I want it to blow backwards, at least somewhat. So what do? Well, we go back to our dot product here, and I'll say we need to change this value. We're getting values from -1 to 1 right now. Really what we should want is the lowest value that this whole operation should return should be 1, meaning be what you were already doing, because 1 times anything is itself. So we're going to use a range, a fit range, to say the lowest value that we could get out of here is 1. So we're getting the original shape. But the highest value maybe could go higher, like that. So now we're getting an explosion blasting off that way. And I'm going to turn off this color thing because it's making it look weird. Well, I guess the normals are making it look weird too. I'll turn that off too. So we've got this thing. I guess the normals are still jacked up a little bit, but you get the idea. We've got it still spraying back this way and a lot more going this way. Now, of course, we don't want to rely on somebody coming down in here So once again, we'll make a parameter to, instead of setting the 4 here, let's just have it be able to be set. Well, we'll say like reflect scale. And we'll make that be 4, like we just had. We'll want to keep this as 1. We don't ever want this to really collapse this side, I don't think. So I'll just keep that at 1. What we could also do is increase this number, and that will focus it. The more in line that it is with the actual reflection, the sharper that effect will be. Keeping it at 0 is probably fine. I don't think I'd ever really want to do this, but for the sake of completeness, I'm going to say let's point it to that. Source min. It's 0 now. We could increase it if we wanted to. I guess I should name it too. So I'll say reflect bias to bias it along there. Great. Save that. So there we go. So we can box this up. Oops. We'll say this is the reflection mask, where it's only applying that reflection business over there. Cool. So, you know, is getting complicated, but I think it's pretty well organized still. Hopefully you're still following along, because there's one more linear algebra thing to cover here.